One last bit on the use of power spectral density. So in the previous example, what we looked at was we were generating or pretending like we were sampling, let's say, position data, the x of t. But there's some times that we are sampling things like velocity data or acceleration data. If we're using an accelerometer or we're using something that is able to detect velocity directly. But we want to make claims about position, velocity, or acceleration from any data that we have. Well, a nice thing about using the Fourier series by taking our original series and turning it into a Fourier series is the Fourier series is made up of sines and cosines. And sines and cosines are easy to integrate and they're easy to differentiate. So for example, what if we captured position data and then we run it through our Fourier series? Again, what are we getting out of that? Our coefficients, these a values and these b values, an a naught value as well. If we know the a values and the b values, we could differentiate and we can get to our velocity. So again, we're going to know the frequencies after we do the DFT. We'll know omega 1, omega 2, omega 3, etc. Because remember, whatever our fundamental frequency is, that omega 1, every subsequent one is going to be an integer multiple of that fundamental frequency. So W6 is just 6 times W1. Omega 8 is just 8 times omega 1. So we have the omegas and we know the a's. So to differentiate, well, any cosine term we differentiate will become a negative sine term. Any sine term we differentiate becomes a positive cosine term. But also we need to do chain rule so that we have that omega coming out in front. So we can go to velocity by differentiating. Then we can go to the acceleration by differentiating twice. So what we have to be aware of is, let's say we captured accelerometer data. The coefficients we're finding with the DFT from the acceleration are actually not simply the A1s if we were talking about position, but it would be like the negative A1 omega 1 squared. And then the sixth term we would look at is the negative A6 omega 6 squared. So what we have to keep in mind is if we have acceleration and we want to go to the velocity terms, we're going to have to make sure that we are dividing by the appropriate frequencies for each term. If we want to then go from velocity to the position, we need to again divide each of those coefficients by its corresponding frequency, because otherwise we're going to get a skewed value we get when we're comparing the strength of our frequencies.